Hello, everyone. I think I'm going to start. Can everyone hear me okay? I take that as a yes. If I could request everyone to press *6 so that you can mute your phones, that'd be great. And if you have any questions, please go ahead and unmute and then ask the question. Can everyone see my screen? I hope you can. So I'm going to start this session. I think I'm going to go over some few basic information that I went over last week, and then we can jump into Spot. And so I hope you all have the Spot program installed on your machine. So as I'm going through an example today, I would encourage you to work along with me also. So let's start. So we're going to look at Spot today, and the intent today is to not cover everything Spot can do, but go over one key aspect today of Spot. So the agenda is to go over visual comfort briefly for a couple minutes, just to refresh your minds, and then the item that we're going to look at today, as far as Spot goes, is to test and validate if Spot even works. So now I'll go through how to do that. And then finally, I'll have another homework exercise for you guys as well. Speaking of homework exercise, I hope you had time to think about last week's or a couple of weeks ago, our first session's homework exercise. The intent is to just help you think through asking questions during design process. So first, let's go over visual comfort. And this is just a quick overview of what are the 6 key performance indicators that we always want to ask in our project, in our design process, to see whether we have an understanding of energy or performance. And today we're going to focus on visual comfort and using Spot. So defining visual comfort really quick, it's not only the amount of light, but also bringing in balanced light and having no glare defines visual comfort. Again, it applies to both artificially lit and daylit spaces. So how do we measure visual comfort? For adequate light levels, we'll start with daylighting autonomy, and then for balanced light and discomfort light, we'll use minimum daylighting autonomy and maximum daylight autonomy. So daylight autonomy, again, just a quick refresher, is the percent of time over a year at which daylight can provide a given illuminance for a given point. So for instance, if we're looking at a classroom that is designed to achieve 50-foot candles, then 50% DA for 70% of a south-facing classroom means that 50% of the time the design achieves 50-foot candles at 70% of the floor area. The minimum daylighting level is we have to have a balanced light in a space. So at a minimum, actually, hang on a second. Howard Cohen just asked a question. Let me just write to him. So for a minimum daylight autonomy, at a minimum, 60% of the classroom should achieve daylighting autonomy. And then for maximum daylighting autonomy, this is to control glare. Here they're suggesting that we shouldn't be bringing in light that's 10 times more than the design illuminance into the space for more than 5% of the space. So this is just a quick refresher, and I think we'll understand this more when we're using Spot. So today we're going to look at, we're going to try to test Spot. And for test Spot, what I've done is I've actually gone out, we've done a field measurement on an existing classroom. Here's another question. How do we set the design DA criteria? Design illuminance comes from IESNA standards. So depending on the activity of the space, we can choose to design illuminance from the IESNA standards. And for typically for classrooms, the type of activity is reading. So that calls for a 50-foot candle. Okay, so I'll continue. So there are 6 steps involved in Spot, and I'm going to focus only on a few of them today. And as I mentioned before, this is even though it's a simple user interface, it has a lot of different features to it. So I'm only going to focus on a few of them today, and then the next session we'll pick up the rest of it. So today we're going to look at the project info, how to set that up, and geometry. This is where the bulk of Spot usage is. So we will look at geometry today, how to input room, windows, lights, and such. And then we'll also look at site and usage. And then under the design tools, we'll specifically look at annual daylight performance. We'll wait until next session to look at night light performance and photosensor location analysis and such. And also the predicted energy savings analysis, we'll wait till next session to look at that. So today, what I want to show is how do you build a classroom in Spot. So the example I have here is schools that we have currently under construction. Actually, it's been occupied in Scottsdale, and what you're looking at here is a classroom that's facing north, and a couple of windows here, and I'll show an elevation in a second. And here's the reflected ceiling plan with light fixtures laid out this way. And the teaching wall is back here to the west, and the door is on the southeast corner here. And here's the actual space, and you can see a low window for vision right by the teacher, and a high window, really big window for daylighting. So this is what we're going to test in Spot today. And if you see the elevation, here's the clip of the elevation for that particular classroom, and this is in the second floor, by the way. So here's that huge window. It's about 12 feet by 4 feet long, and here's the small window, vision window. It's about 6 feet by 1 foot 8 tall. And in general, the classroom is about 9 feet tall. The ceiling is at 9 feet, and it's about 80% reflectance on the ceiling, and I'd say roughly 60 to 70% on the walls, but it's pretty much white. So that's the given condition. So we went out there on March 26th around noon, and we took some measurements for this particular classroom facing north. And it's actually tilted 14 degrees towards the east, so that's something that's important to know also. So we did some field measurements, and we basically took 2 columns at 10 feet. This is a 30 by 30 classroom, by the way, and we took basically 8 points of reading, and column-wise they're spaced at 10 feet, and rows-wise they're spaced at 6 feet each. And as you can kind of intuitively say, at noon, because of the large window here, there's about 50-foot candles and 17-foot candles here, and then just goes down to 7 and 9. So this is what we're going to test today and see if Spot produces the same result as it is here. Okay? So let me get over to Spot. And I hope at this time you'd be able to open Spot and use the program along with me. So the first and foremost thing that we want to do always is to enable macros, because even though Excel is the front end, the back engine is Radiance, and in order to have a lot of these formula work, we have to enable macros. So I would typically call this some example. Typically, I would try to put this in your project folder, but for this instance, I'm just going to put it under my documents. Okay, and we want to use English units, and today we're going to look at Spot daylight autonomy, and we'll look at the rest of the stuff later in this session. So report type, this is key to set this right in the beginning. So you want to set it as Spot daylight autonomy, and that's pretty much it. That's the first step. It's pretty straightforward. And then if you hit begin project, it'll just give you a warning that everything will be based off of this daylight autonomy criteria. And then as soon as you do this, it'll automatically create a folder under the project folder that you save this file, and then that's where it's going to dump all of the associated files for this particular project. So we're going to look at geometry input today. And it's a 30 by 30 classroom, and I'm going to refer back to this floor plan right here. So it's a 30 by 30 classroom, and it's got a couple of windows here. So let's define the space. So 30 by 30 classroom, and the ceiling is actually 9 feet, and the ceiling is flat. And you can, I believe you can give different orientations on this, or slope ceilings. Work plane height, this is something that that's common in the industry. Work plane, typically our work plane is at the desk level, which is 30 inches, so 2.5 feet. And wall thickness for now, let's assume it's a stud framed wall. And really this plays an important role if you have a really deep wall thickness, because it'll account for the associated shading that you get from the wall. But for our instance, we'll use it as 10 inches, and I think that's really close. And the skylight depth part, that's only if you use a skylight, so let's ignore that for now. And this is the orientation, and you see here on the compass dial here, you see that orange wall is the south-facing wall, and right now the north is, true north is set to the north wall. So we know it's 14 degrees. So as soon as I do 14 degrees to east, this is very close to what the real life it is. And on our image, we saw, let's see, the carpet was kind of dark, so I'm going to leave it at 25%. But the walls are more than 50% because it's pretty much white. You can take into account a little bit of all these distractions that are hanging on the wall. But for now, I'm just going to call it 60%. And the ceiling is 80%, and that's the default, and I think that's an 80% ceiling. And let's see, from the photos, it's kind of hard to say, but and I think the mullions are kind of a darker color, so we can assume 50%. And at this stage, I wouldn't worry too much about the ground plane. We don't have any light shelves, or we don't have any overhangs, so let's ignore this part. So that's pretty much it. That's the basics of the space. And just a quick legend here, and here's the space. That's the south wall. South wall, that's in orange. And then that pink line is the work plane at 30 inches from the floor. So that's basically our space. So I would always try to save this as often as I can. because just like any other program, Excel sometimes will crash if you have the wrong formula in or wrong input in. So it's a good idea to save it all the time. All right, so let's define our openings and overhangs. We don't have any overhangs in this case. It's just in our north-facing classroom. So we just have openings right now. So the first and foremost here, we want to select which wall we want to add opening to. And in this case, it's the north wall. And then I want to add a window, and not an overhang or an interior light shelf. I want to add a window. So the window number, this is just for Excel to understand what windows or what openings we're putting in. So right now, oh, by the way, if you see a little tooltip in Excel, you can just you can just mouse over, and it'll tell you what it is. So window number 1, and I know I have a plan in front of me with some detailed measurements. I'll go over this again. Okay, so I'm going to model this little tiny window over here, and I know it's 2 feet 8 inches from the wall, from the left wall. So it's starting. Here's your orientation. So that's where you start off on this wall. So from the left wall, I know it's 2.66, which is 2 feet 8 inches, and the sill height is 3.33, which is 3 feet 4 inches, and I know the window height is 1 feet 8 inches, so that's 1 foot 6, and window width is 6 feet. And the transparencies in this particular project, they're using solar band 60, which has a light transmittance of 70%. So I'm going to use 70%. And then window treatment, as you noticed on the photo here, there is actually no window treatment, no blinds or anything on that. So for now, we're going to call this none. And so N for none. That's it. You got your first window defined. So if you want to go to the second window, I'll pull down window number 2, and the distance from the left wall. Go back. I know this window is 7 feet apart from the other window, and that's 6 plus 7, 13 plus 2.5, so 15.66 feet from the left window, and the sill height is 5 feet. The window height is 4 feet. Window width is 12 feet, and the same solar band 70 or solar band 60 is used, and that does not have any window treatment either. So there it is. That's our openings on the north wall. This is pretty straightforward. It's very simple. And again, I would save this as often. Just to make sure that whatever we've given in as an input makes sense, we can always run this Run Interactive View. So I'm going to click that. It actually will show a really quick rendering of what this space will look like. And this is again because of that Radiance engine that's behind the scenes. So if this doesn't look to you as right, so you have an opportunity to go fix it. So that's why it's really useful to use this rendering interactive view. Oh, and by the way, I want to show that you could actually move into this space, and you can kind of see back and forth if you want to look at different views, and then you can go forward or left and right, or you can go forward, you can go backward, and you can tilt the camera up or down. Actually, I'm too up now. But anyways, so that's the advantage of this. And you can also roll the camera left or right and change the pitch on it. So this becomes a really useful tool while we're designing this classroom here. And it'll save this in the folder that you created, so you can always go back to this picture file. The only disadvantage that I've found with this picture file is you can't save this to a JPEG or anything like that. So you'll have to use it as .pic format. All right. So So we've defined our geometry and we've defined our openings. So now I'm going to go to electrical lighting. So if you look at this, they have 3 by 3, 9 troffers basically mounted on the ceiling, and these are downlights. And they have 3 lamps in them, and they are T8s. So how do we model that? So we're going to call this electric lighting array A. And then under luminaire, right now I don't have any luminaire, so I need to go add one. So if I add a luminaire, this is typically where you would define exactly what that luminaire is. But for this instance, I'm going to choose the spot generic again, and we'll come back in our next session and show how to select exact luminaires based on what our electrical engineers specified. So spot generic, and the type is a linear fluorescent. And as soon as you do that, it will pull the default generic light fixtures. And I know it's not a pendant; it's a troffer, and I know it's not a parabolic louver, so it's just a normal troffer lensed 3-lamp T8. So as soon as you say that or select that, luminaires currently in the project, it will be here, and then you can go back, and this will appear on this list to choose from. So now I'm selecting troffer lensed 3-lamp T8. And for now, let's ignore this auto center and leave it as off. And zone is important to understand. If I go back to the reflected ceiling plan, the way the daylighting sensor in this particular classroom is designed is to control this first row of light and this second row of light. So the third row of light does not get controlled by the zone, by the photocell. So from a photocell dimming standpoint, we would call this as zone 1, these 2 lights, 2 lamps. If we want to get really accurate, we could call these 2 rows, this first row is zone 1, and the second row is zone 2, and the third row is zone 3. But for simplicity, I'm going to call the first 2 rows closest to the window as zone 1. So that's zone 1. And then mounting suspension. If you look at the little tooltip here, it'll tell you that if it's ceiling mounted, then or recessed luminaires, you should put 0 for that unit. But if it's a direct indirect light fixture, then you can say from the ceiling how far down it is. It's typically 1'6" for direct indirect fixtures. But in this case, it's 0 because it's recessed. And then so now we're trying to define the layout of the lighting light fixtures. So you notice here again it starts from this corner, from the left-hand corner, south left-hand corner. So that's 0, 0. So I'm going to define these 2 rows of light fixture. And even though the light fixtures are this is a 4 by 2 light fixture, when you're defining its in spot, you always go to the center of the light fixture, and that's where your coordinates need to be. So in our instance here, the row should start at 1, 5, 9, 13 plus 2, 15 feet. And then the column should start 2 feet, 4, and 5 feet. So the row starts at 15 feet, and the column starts at 5 feet. And number of rows, I have 2. Number of columns, I have 3. And row spacing. The row spacing is 4 plus 4, 8 feet. And the column spacing is 2, 4, 6, 8, 10 feet. That's the column spacing. And then the orientation is if you leave it at 0, it'll be parallel to the south wall. So I want to call it as 90 degrees. So as soon as I hit enter, I can see those 6 light fixtures put in. So let's define the second array of light fixtures. Again, we'll select the same light fixture, and we'll call this zone 2. Mounting suspension again is 0. Now the rows should start at 1 plus 4, 5 plus 2, 7 feet. And the column should start again at 5 feet. Number of rows 1, and number of columns 3. Row spacing, it really doesn't matter because you only have one row. Column spacing is 10 feet, and the orientation is 90 also. So we've defined our lighting layout. Before we go further, again, it's a good idea to save it all the time. And then before we go further, let's run an interactive view. So this will tell you really quick that your input is correct based on this photo here. Okay. Again, if you want to save it, you can. So let's go back to this. So that's pretty much it. So now we've defined the geometry, we've defined our the openings, and then we've defined the electrical light fixtures. Okay, and we'll get into these advanced options next session. So I then hit next. So while this is calculating the electrical lighting calculations, I'm going to minimize that. This is the site and usage input. So this is pretty straightforward. We're in Arizona. And then even though this is in Scottsdale, from a sun standpoint, Phoenix is pretty close. So I'd use Phoenix. But if you really want to be really accurate, you can just choose these latitude and longitude for Scottsdale or for that particular site, and also the elevation and the other information. So from a legend standpoint, here's the annual schedule. And this is really important to understand the impact of daylight throughout the year. So O stands for occupied and U stands for unoccupied. So the default is for a 9-month school. And as you notice here, the school is not occupied during the first week of January, at least in this example here, and it's off during the summer, and it's off again last week of December. So this is the standard schedule that comes out. But if you want to change something, and if you think we will have occupancy starting the 3rd of January, so you don't want to do 0, you want to do O for occupied. You can easily change that. So that's the annual schedule. Then as far as each week goes, here's on the left-hand side you have the weekly schedule, and as you see, hours on the left and weekdays on the top, and so 1 means 100%. The lights will be turned 100%, and point 3 is, as you can see here, in the weekly schedule, lighting load less than 33%, and then if it is between 33 and 66%, which is during lunch hours, there's a slight change in color there. So, and again, this is trying to say it's from 8 o'clock to 4 o'clock. That's when the school will be occupied. And if you want to change any of these numbers, it's pretty easy. You just change the numbers here. Okay, so that's site and usage. And then, so let's move on to the next one. So it's going to start doing the daylighting calculations. So while it's doing that, let's review our nighttime artificial light calculations. So based on the light fixture that we chose, the design illuminance for reading activity in a classroom is 50 foot candles. And light loss factor is a factor that's associated with the light fixture type. So that takes into account the amount of light that's lost because of the fixture design. So 0.85 is a pretty standard number, so leave that alone. And if you notice here on the right-hand side, here's the crude representation of the plan, which is 30 feet by 30 feet. And again, this is Excel, so you have to work with that. You notice all the foot candle displays here for every single grid. So technically, this lighting design is overlit, because if we're trying to shoot for 50 average, we're seeing a lot more than 50 in most of these spaces. So in our next session, we'll come back to the actual light fixture that our designers have used and use that instead of a spot generic light fixture. Okay, and this is just a 3D graph that tells you how the light levels are. So while we looked at this, it cranked the daylighting calculations, so we can go into next, and we'll do one more for the annual daylighting performance calculations. There it is. All right. So on the right-hand side, this is where it'll show the luminance levels. And on the left-hand side, you see Zone 1. We defined the first two rows closer to the window light fixtures, and Zone 2 is the last zone. So here you see different design conditions: clear sky, overcast sky. So when we took this picture, or when we took this meter, our levels, light levels, it was pretty clear sky. So we're going to use this top portion of the chart here. And then March 26th is very close to the equinox, March 21. So and then we were right about noon, so 11ish to noon. So I'm going to select this particular one. So equinox, 12 p.m. And if you look at this, we have this display of amount of foot candles. So let's cross-check this with our actual readings. So if you look at the actual readings here, so that's taken at 10 feet from this wall and 6 feet from that wall, from the north wall. So if you go back, so each of these grids are at 5 feet. So 6 feet from that wall and 10 feet from this wall. So that's really close to what our actual condition is. And likewise, let's go to the next one. This is 17 foot candles. This is 6 feet again from the north wall and 20 feet from the east wall. So if I go back to that, 20 feet is 5, 10, 15, 20 feet, and then 5 feet, 6 feet. So that's right about there. So this proves that, So this proves that a spot predicts very close to what the reality is, and as you would expect, closer to the window, you get a lot more light, as you can see from this photo. So that was pretty much it, and I have a few more items to go over for today. So if you want to unmute and ask any questions, if you have, I can start answering them. And then on the left-hand side, you see you can check at different times of the year. Summer morning, 8 o'clock, you see what happens to this lighting here. And summer at 12 o'clock, there's plenty of light. And again, remember, this is tilted 15 degrees to the east, so you would see more light coming in at 8 a.m. because of that tilt than at 12 o'clock. Because 12 o'clock, this is facing north, the sun is already behind us. And then just to compare between 12 o'clock at equinox, we got about 52 foot candles in this cell on a clear sky, compared to an overcast sky, it's 34. So that's roughly losing 1/3 of its light because of the overcast conditions. And again, that information is taken from the weather file for Phoenix. So does anyone have any questions so far? take that as a no. Please unmute your phones, and I look forward for some feedback. Was this pretty simple, straightforward?
Yeah, I think it was good to walk through an example just
Okay.
to see how we would actually use it.
So I'm gonna tell you that this design is actually not adequate design when it comes to daylighting, because we can look at this. If you hit View Report, and we're using Spot Daylighting Autonomy report, and if you go down, it says it's really poor daylighting. And the reason for that is we looked at daylighting saturation and then maximum daylight. There is no glare because there's no direct light coming through. And if you look at this on the left-hand side here, Zone 1, the average foot candle is 37 foot candles and the maximum is 342 foot candles. So this does not exceed the max DA number, which is 10 times 50 foot candles, which is 500 foot candles. So we're not exceeding that. So there's no glare issue. But the problem is there's not enough light throughout the space. There's enough light in some parts of the space, but not more than 60% of the space. So that's your challenge with north face. So the solution that Spot suggests you to do is to change the amount of light by increasing the number of windows or changing the glazing transmittance. We already have a really high glazing transmittance, which is 70%. So if you want to make this a much better daylit space, then we should have a lot bigger window than just this. Does that make sense? And here's where I want to show, if you use another metric, for instance, let's use lead single point in time, and it'll automatically start. It'll give you a warning that says you have to have glare control. In this instance, the glare control. If you say no, then your lead results will fail automatically because lead requires you to have a glare control. It could be as simple as just blinds, but you need to have that. So for example, I'm going to say yes. Then if you hit continue, again, look at this. This is using sunny conditions at the equinox at noon. So here's the floor plan, and here's the plot of foot candles, and you see only 33% achieves 25 foot candles or greater. And LEED's metric is different than the design illuminance. LEED looks for 25 foot candles, and as long as you have 25 foot candles, and that will be counted towards your amount of square footage that achieves that 25 foot candles. And I think in schools, if you get 75% of all of your classrooms achieving 25 foot candles and above, you get 1 point.
Hey, Prem?
Yes.
So can we work backwards? Can we use put in the optimum factors that we're trying to achieve foot candle-wise and see how much additional window we would have needed?
Unfortunately, you can't. You'll have to play with a couple of different options to see how it performs. And it's really straightforward to do that. So let me just go back. And for instance, intuitively, I think that's because that tiny window that we have on the left-hand side by the teacher is not bringing in enough daylight to the rest of the space. So for now, let's just copy this big window and put it on the left-hand side and see what it does to our daylight. And it's really simple to do. So if I go back, so this first window that I did, let's say it's a copy of second window. It automatically copied it, but then all I have to do is to move it closer to the wall. So now I got two windows. So let me just save this one. and then it'll be a matter of minutes before it finishes this calculation. So unfortunately, you can't work backwards, but it's pretty simple to just change a few things and let it run. So we're not changing any of this.
And/or a higher light transmittance class.
Yes, exactly. Right now we're using solar band 60, which is 70%.
70%.
It's really high visible light transmittance. So give a couple minutes here. It's going to crank this through really quick.
When you say you're saving, it's just hitting the next button. That's the save?
No, the save is up here.
I couldn't see it.
Can you see it
Okay.
now?
Yep. Yes.
It does a series of different calculations. Here's where it actually uses the weather file for Phoenix. And I didn't point that out, but you can actually import a weather file that's specific to your site if you don't see your city in the list of sites. So, Howard, to answer your question, at equinox at the same time, 12 o'clock, you see how much difference that makes.
Yep.
Which is intuitively, that's what we would expect. And then if you hit view report, again, it's remembering that it's we had it as lead at our last iteration. So let's go back to spot daylight autonomy. It still says poor daylight because it hasn't reached the 60% level. If it reaches 60% of the classroom, gets that 50 foot candles of light, then that's when it'll say adequate daylighting. So as a rule of thumb, if I go back to the very first screen, see right now the window to wall ratio is almost close to 40%, right? Which is what the code maximum is for commercial buildings, 40%, and you can exceed that. And so this is where it's important to define how far do you want to do daylighting. In this instance, if our goal is to daylight the entire classroom depth all the way till here to the back end of the classroom, then you need more than 40%. But if our intent is to offset 2/3 of the classroom, then probably this is good enough. So that's why it's important to define how far do we need to do this. How far do we need to have daylighting? And this will be a different story if you have south classroom. I mean, if this classroom is actually facing south instead of north. And again, that's very simple to test. Also, you just all you have to do is actually technically you have to go change the south wall here and add windows to the south wall. So that's pretty much it for today. And I have a few more items for next week on how to integrate photocell locations and such, and we'll go over that next week. And it's actually really it will be really interesting. So as far as the homework goes, I would like you guys to just take one rectilinear space in any one of your projects, and if it's a classroom, that's great, and just model the geometry and use the default spot luminaire for electrical lighting, and then test it against the performance. And from a daylighting performance standpoint, you can easily check that if you have a light meter in your office. And if you don't have a light meter, actually there's an app for iPhone that will tell you what the light levels are. So it's very easy to find out what the daylighting performance, the light levels in a space is. So that's that's what I'd like you to work on for the next couple of weeks, and then we'll reconvene again in 2 weeks. So I'm going to call this done. If you have any questions, anyone?
Thank you, Prem.
Yeah, thank you. Do you think this will be useful?
Yes. Absolutely.
Very good. And it's pretty straightforward, at least the daylighting part of it. And the next session, we'll go through integrating electrical light fixtures. I think that's where we need our lighting designers' expertise when it comes to integrating photocells and light fixtures and daylighting. So from an initial daylighting design standpoint, it's a really simple tool for architects. All right. So if you have any questions, feel free to shoot me an email. So I hope you'll use it in the next couple of weeks and just play with this program before the next session. All right?
Thanks again.
Thank you, guys. Bye-bye.
Thanks. Bye.